Welcome back, everyone. Here's Dale from ClickHouse for the next talk. So, take it away.
Thank you. Can you hear me? Perfect. Hi, I'm Dale. Thanks for the introduction. I'm part of the product team at ClickHouse, focused on observability. And I'm going to talk about how we built an open source observability stack that you can just download and use. I'm going to talk about the design decisions that we made. These design decisions were actually made before this stack was part of ClickHouse. So in April of this year, this product became part of ClickHouse, but the actual decisions that we made were made prior to that as part of the team that was separate. So I'm going to more talk about the design decisions that we made independent of ClickHouse in trying to build an open source observability stack that people can use. So before I start and talk about that stack, I'm just going to talk about quickly what ClickHouse is. Who in the room knows what ClickHouse is? That's pretty good, actually. So we're an open source column-orientated OLAP database. What does that mean? Well, if you think of Postgres as being an open source database that you use for transactional data, ClickHouse is an open source database designed for analytical data. So we're column-orientated. That means we're fast for things like aggregations, but we don't offer things like transactions, and point lookups as a fast. And we're fully replicated. We mainly get used in analytics use cases, but observability in our mind is just another analytics use case. So we also get used for observability use cases. People build on top of us. There's plenty of open source offerings built on top of ClickHouse. There's also commercial products that are built on top of ClickHouse. It's pretty ubiquitous at this point. If you're looking to build your own observability tooling, you probably use ClickHouse to store your logs, your metrics, and your traces. We were open sourced in 2012, and we've been around. We've got about 45,000 GitHub stars at this point. If you're interested, just go to GitHub/ClickHouse. We've got about 1,200 committers. So it's a huge project. You can download it. It's Apache 2 license, and you can just run it on your own self-managed hardware. So ClickStack. So what is ClickStack? So this is the stack I'm going to talk about. It's an open source observability stack. So it consists of three core components. ClickHouse in the middle is the database. That's the engine. For many of you, you've probably heard of something like the Elk stack. It looks very similar. Replace Kibana with HyperDX, which is the visualization layer. And then the ingestion layer, instead of being something like Logstash, is OpenTelemetry. So it's OpenTelemetry-native, and it's designed such that you can just deploy this stack in one command, or you can deploy it with a Helm chart as well, and you have a stack that's opinionated and that just works with ClickHouse. So prior to this, people would build their own UIs on top of ClickHouse. The idea here is that you just get something out of the box that works with the UI for logs, traces, and metrics. The HyperDX UI, which I'm going to talk about why it was built on top of ClickHouse, became part of ClickHouse, the company, in April. But the decisions that we made in choosing ClickHouse were made independent of being part of that company. So those decisions still hold true, and that's what I'm going to talk about today. So when we built HyperDX, the UI, we were trying to choose a data store. And we had a few options, a few choices at this point. We wanted this obviously to all be open source. So we thought about building on top of a search engine, first of all. Maybe we build on top of something like OpenSearch. And we looked at the workload and the types of problems that search engines, what they're good at and what they're not good at. They're great for those kind of needle in a haystack searches, for log searches, but they're less great if you want to do aggregations over wide time periods. And they're extremely disk usage. There's a lot of disk space. And if you need to do aggregations over high cardinality data, it's not really what they're designed for, but they're great for logs. So then we thought, well, maybe we could also build this UI and have the search engine for logs, and then maybe we just do metrics and traces in some other data store, which is designed for those. So maybe we use a metric store like Prometheus, stronger aggregation performance, but doesn't really provide that search capabilities. And if you want to aggregate across time series, it's not really designed for that, so it forces you down quite opinionated workflows. And we wanted to design an interface that was very exploratory, so people could just do any aggregation they wanted, visualize anything, and not have to go through just metrics to traces to logs. So that really wasn't kind of an ideal fit, and we also didn't want to have to distribute an open source stack where there's two data stores that people have to manage. So about the year previously, we spent a bit of time looking like what could we use here. So we wanted something that was Good for search, offered decent search performance, had lightweight indices, ideally had that inverted indices support, but also offered strong performance, aggregation performance. And last, one of the characteristics that we wanted, that we saw increasingly, that people wanted to store their metrics, their logs and their traces on object storage, such they didn't have to think about retention. And they could store potentially infinitely for relatively cost efficiently. So we wanted something that was cost efficient, fast, and had fast aggregations, and a few other requirements. So we wanted resource efficiency. We obviously wanted fast insert performance, fast aggregations, support for high-cardinality data, which is often a challenge for metric stores. We wanted schema on read. Some of the team had previously worked with Splunk a lot, and one of the things that we liked about Splunk all those years ago was that you could actually just define the schema at read time and pull the schema out. You didn't need to define it up front. But we also wanted schema on write, so that if you just send semi-structured data, the properties of things like OpenSearch and Elasticsearch, where it just creates the schema for you, were quite nice properties as well. So ideally, it would support that. Then we wanted expressive query language, support for object storage, and most importantly, open source. So we decided on going on using a columnar storage. Now we chose ClickHouse. There's a number of other columnar storages out there. You may be aware of, there's several others, things like Druid and Pinot. These justifications, I think, apply equally to them. It's really just down to which of these column stores you want to use. At the time we closed ClickHouse, the license was appealing, and it was pretty easy to get started. So what is a columnar storage, and why is it good for this use case? So typically, if you're not familiar with what columnar storage is, row-based storage looks something like this. With columnar storage, you basically store, instead of storing all the data in row orientation, you store it in column orientation. So every column is written independently. And then you ideally can order that data. And if you can order it, then it will. You can also apply things like codecs. So here we've just taken a delta codec and just said, rather than store the date, we just store the difference between the dates. That improves the compression, reduces the amount of data we need to store. And most importantly, that allows it to compress really well. So that was one of the attractive things. But one of the other attractive things is that with a column store, you only read the columns that you need. So you've got less data to read because it's compressed, so less I/O. And when you query, that is ideally orientated for aggregations. So you get fast aggregation performance. And when I talk about aggregations, I mean basically like charts in observability. So some attractive properties there. Most column stores also, because the columns are independent, you can parallelize the execution. So when you issue a query, it runs across all of the cores on the machine, rather than tying the parallelization to how the data is orientated. For example, in sharding, it's just done at a block level. And most importantly, we also needed something that was a multi-node, where it could parallelize across the nodes, and you could shard it, and it could all come together on one coordinating node. So some attractive properties with regards to just using the full resources of a machine to answer a query. And then a lot of column stores, how do they filter? Well, as a pretty common access pattern in observability, you're looking for all the error logs or all the logs for a certain service. They typically have like a sparse index on top of them, where basically they just store the data in blocks. The data's ordered, and then they store the first value of each block in memory. So when you search, you can scan to that index and say, right, I only need these blocks. And that just means you only read a small subset of the data, which is already highly compressed, so you get fast read performance. So there's an example of this is Stack Overflow data, but the same applies for any, the same applies for any data set, whether it be logs, metrics, or traces. It's all just row data. So you see the order by here determines the order of the table. And then when you issue a query and say, I need everything from this column or this date, then it's fast to scan in and identify the blocks that we need to read. So we only read a small amount of the data. So again, attractive. Most column stores now also, or columnar databases also support JSON. So you can just send JSON and it automatically, and JSON maps quite nicely to a column store because JSON keys are basically columns, and rather than storing it as ND JSON, you're kind of orientating it up the other way, and you can store the data in columns as well. And in ClickHouse, and I'm sure this is the case in many column stores, but when the data comes in, if it hasn't seen the column before, it'll just create it for you. So that's an attractive quality, especially in things like logs, where you're taking data from, for example, Kubernetes, and the tags are dynamic, and you can't predict the schema up front. You need that kind of schema on write property. One of the attractive things specifically that we found about ClickHouse was this type delineation, the fact that in some NoSQL databases, when you send a log, it determines the type of the field based on the first value it sees. What ClickHouse does quite a little bit differently is it just says it creates a separate column for every occurrence of that field and the type. So if you send it as an int, you get that column .int. If you send that column as a string, you get .string, and then you can cast at query time. And that's just quite nice if you just need to chuck data in. And then S3 storage. So being able to store stuff on S3, on object storage, means that theoretically you can separate storage and compute. So you just chuck all your logs and metrics on S3, and then you can scale the compute dynamically. Again, a really nice property. It means you can isolate your read and write paths. We can have a small pool of compute for our inserting our observability data. And then when we need to do an investigation, we ramp up our read pool, which is separate. And then obviously if the data is compressing really well, object storage, pretty cheap per terabyte. You can theoretically retain things for a really long time. If you're not querying it, you're not using resources. So some of the reasons, so cost efficient and scalable, the column orientation and the fact that you're ordering the data is really friendly to compression algorithms. So we can compress really efficiently. That's attractive. Fast aggregations, because the data is orientated by a column. When we read a column, we're just reading it, streaming it into memory. So it allows for fast aggregations, effectively charts render quickly. Fast filtering, again, something that we needed. Fast writes and space-efficient indices. So I should say that, I didn't really mention this, but for the search component of this problem, columnar stores also support indices like inverted indices at a columnar level. So it gives us that search behavior that we wanted, the same as OpenSearch or Elastic. So we've got that there in one store. And then we've got these schema on write capabilities through the JSON. Schema on read, most columnar databases effectively support SQL. SQL has a whole range of string analytical functions that you can use for parsing those strings. So if we want to do schema on read at query time, and we've got a big string blob and we want to pull a value out, we can still write SQL expressions. And as I said, SQL native. Now, the problem, this is where we hit a kind of, for us, this was a little bit of friction. So SQL's great as an analytical language. I think it's been around so long at this point, everyone agrees it's not going anywhere. It's great for analytical queries. It's great for BI. Is it really the natural language to go and query as an observability data as an SRE? We didn't think so. So that was really, there's a few examples here of other companies that have built their observability offerings and their UIs on top of columnar stores. So there was lots of evidence out there as well. But back to the SQL point, we didn't feel that was a very natural way. Like it is if you want to do really advanced analytics, but it's just not a natural way to query. Splunk SPL was a great language. Elasticsearch has a great natural language for querying with just like natural language queries. So we felt that maybe we needed something to bridge that querying gap unless users really wanted to go deep. So I'll talk about that in a moment. Before then, OpenTelemetry, I'm sure everyone in the room knows what OpenTelemetry is for our ingestion layer. It was pretty clear that OpenTelemetry is pretty much the de facto standard for ingestion. We didn't have time, honestly, to go and build a whole suite of ingestion tooling, so we piggyback off that community, contribute there, and the fact that it's also open source means that you can switch stacks quickly, kind of tied into our ethos of being vendor neutral and no lock-in. We built the stack such that the UI, such that it is OpenTelemetry-native. If you're using OpenTelemetry, it's a lot quicker out the box. It just works because it knows the schema and it knows the column names. If it's not OpenTelemetry data, you can just, we made it such that you can still configure the UI to say, like, this is the time, this is the date field, this is the error field, for example, so that we're not tied into that schema. And at the end of the day, observability data is just kind of rows and keys as JSON values. So we tried to make that as OpenTelemetry native, but not OpenTelemetry exclusive. So a lot of people use Grafana with columnar databases for observability, but we wanted to build something where the interface was a little bit more tightly integrated into actually more tightly integrated into the database. And the reason for this is that, for starters, if you use Grafana with a database, you have to query in SQL. To that point, that's not very friendly for SREs. But also, we felt that, like, even if you could write SQL, it leaves you to write efficient SQL. Query analyzers are pretty good at optimizing the SQL, but it's pretty easy to write a very inefficient SQL query. So we wanted to provide a UI which was tightly coupled into the database and used it in the most optimal way possible, whilst also providing as many open workflows as possible as well. So we felt that it was worth building a dedicated interface. As I said, you can't expect people to write optimal SQL queries, even if they can write SQL queries. As an example of querying ClickHouse actually with SQL, it's just not a very quick and easy language to write and use if you're doing log analysis. So we built the UI. This is a screenshot of the UI. We effectively support Lucene query syntax, and we transpile that into SQL. And then we provide filtering, etc. But at no point is the user in the interface having to interact with actual write SQL. Now, if you note in the top right, we do provide the ability to switch over to SQL if the user wants to, but in many cases, users just want to write. They're familiar with Lucene syntax, and it's a pretty great language for querying logs and also trace data. And then I said we have that escape hatch if people need it. Likewise, not having to actually understand what the functions are, all the function names in SQL, how to do a group by, how to do, for example, a rolling average. All of those need window functions, for example. It becomes quite complicated. The UI we tried to build such that you can just do everything through a query builder, and you just abstract it away, while still making sure that the SQL queries we generate are as efficient as possible. So, and then maybe this is the main reason is that it became quickly apparent that the database and the UI need to be tightly coupled for optimal performance. There are queries that there are access patterns that are just faster for column-orientated databases than others, and you can quite easily write queries which just are not friendly to the database. So when you're designing a workflow for the user, we try to think about, well, what load and how will this work on the actual database, and how can we optimize these queries as quickly as possible. So just to give you some examples of some of the reasons and the justification for this. So when you create a table in a column database in ClickHouse, you create an ordering key. As I talked about, it determines how the data is ordered on disk. And if you're grabbing rows for that table, if you know the ordering key, you can write the query more efficiently to minimize the amount of data that you scanned. So you need to understand the schema, you need to look at the ordering key, and then you need to write the query versus just kind of issuing a generic query and hoping it works. Another one, so one of the ones that we came across pretty early was that on a UI, where people are searching across a very wide time range and they're searching for logs, for example, over 2 days. We build a histogram, probably see that in something very similar in Kibana. You've got two options there. Either you can issue one huge query and just bucket across the time range and wait for it to come back, or you can take the approach that we decided one was, let's start building in chunks effectively. So let's chunk that up and issue it in chunks, and then build the line effectively with multiple queries. Now, this has a few advantages. The first is that it means that you start seeing the logs coming back and the histogram filling out in increments, so you get faster time to interactivity, but it also amortizes that cost of computation and memory and load over time. So rather than putting it all into one heavy query, you're just bucketing it up with lots of smaller queries, and that's just more friendly to the database. So what does that look like? Well, this is an example of switching the UI to over 2 days, or 7 days in this case, and you can see that it builds the line out incrementally. And these kind of things you just can't do unless you really couple the UX with the database. So another type of optimization. So in ClickHouse specifically, if you have like dynamic attributes, you can store them in a number of ways. So things that like columns that you weren't aware of up front, you can either put them into the JSON type or you can put them into the map type. Now, if you access that column, log attributes, which has got all of the Kubernetes label on it, it reads that whole column. So what you can do in the schema is you can say, right, well, actually pull that value that I need, in this case, refer it out onto a base column of the table and keep it there, such that when you can read it independently. Now, what we do in the UI is if someone queries the log attributes for the referrer, we detect that and we go to the column that's been pulled out because we understand that materialized column's there. So again, these are like small optimizations, but that log attributes column can be pretty huge. People can chuck lots of rubbish in there, lots of columns they don't need. If we pull them out, into the base table, then those queries will run a lot faster when someone queries referrer. So in summary, observability we think has evolved beyond search engines and dedicated stores. We think columnar databases are the way forward for storing observability data. There's lots of evidence for companies like Netflix and Anthropic that have gone and built their own observability solutions in-house with their own UIs on top. And they've done that by coupling their UI tightly with these databases. And we hope that ClickStack, HyperDX just allows everyone to benefit from that versus just expecting users to go and build their own UIs, which for many of us is just not realistic. And we think that though SQL remains the lingua franca for data exploration, we need to provide these friendly interfaces on top. I've got a few minutes, so I will just show quickly what this looks like, if I can. I think I didn't. But if I start HyperDX or I start ClickStack, it's just one Docker command, so I can start it like this. And if I go back to my table, so it's just one command. And then that's pretty much it. So that's as simple as it is to get started. If you want to go and play yourself and have a look at what this looks like, if you go to play-clickstack.com and you connect to demo server, you should be able to have a play with this data set. So this is a public data set, and you can go back, I think, a day, and you can see this data. And you can see here there's about 500 million rows here, and you can have a play and query this data. So that's what the product looks like. As I said, it's all open source. You can download it. The UI is MIT licensed, which is very permissive, and the database itself is Apache 2, and obviously OpenTelemetry is Apache 2 as well. So that's it. If you've got any questions, happy to answer. I think I've got a... Thank you.
Just a quick question. What about RBAC?
So we're building it. We don't have it. It's at the database layer. We have RBAC support at the database layer. But at the moment, when you connect to the database, you require everyone to kind of connect with their own credentials. We're going to solve that problem and bring database permissions and make sure that they're reflected in the UI. That's probably our biggest task internally right now, is to add RBAC permissions to the UI. Yep.
So is that, on what level then were you planning to implement it?
So I think we're trying to make that decision now. I think the idea will be there will be groups, users and groups inside HyperDX in the application layer, but you'll be able to associate those with roles and permissions at the database layer. So there'll be some sort of mapping. That was our initial thoughts, but it's slightly subject to change because we have a cloud-hosted version of ClickStack, and we need to make sure that what we do in the open source works for the cloud. So there's some details there, but roughly there will be some form of mapping between application permissions and database permissions. Okay? Yeah, we can talk about it.
Yeah, thanks for the talk. I have two questions, actually. One of them is you actually put a reason for the user interface that it needs to be tightly coupled with which I agree, but Kibana happened to be Grafana. Grafana, then there is the Perses in CNCF. I have seen Victoria Matrix as putting a user interface. Did you consider Perses or general open source contributing there? And
so it wasn't. When the UI was built, when Mike, so Mike's not here, he would normally be talking. I'm covering for him, I should say. When Mike made the decision, I don't think Perses was really available at that point. And he just wanted to build something opinionated from the ground up. As I said, he open source licensed it as well. There were some other choices, and we still think Grafana, by the way, is a great tool, and I still expect Grafana to complement this. You can use Grafana against ClickHouse. It's a different use case. It's really strong for dashboarding. The user interface that we have is more designed for data exploration and being able to connect logs and traces and just being able to explore, and it's really optimized just for ClickHouse. But we have plenty of people that are using this UI and they're using Grafana because they have other data stores they want to connect to and want to correlate data with. There was a decision whether we could have potentially built the application inside Grafana. That was an option. Maybe we could have built something. Yeah, but the license there wasn't really friendly to us, and Percy's unfortunately wasn't available, which, by the way, is fantastic if you're part of that effort.
And the second one is about this, the Cyansafe observability stack has decided SQL to be the common query language.
Yeah, we saw the...
Yeah, I would like to get your comment on it.
I only saw that, I think I saw that earlier in the year. We're not actively engaged there yet. I think we have some people that we'd like to meet at KubeCon in the US this week to discuss that further depth. I don't have a strong opinion personally. I think it's a great language from which people can build interfaces on top of. I don't think it's the language that's natural for SREs to query upon until they're doing really deep advanced data analysis. But we probably will look to try and contribute where we can.
Is there one more question? Have room for one more? If not, then I want to thank for your talk.
Thank you.